Here we are at the physics video lecture. Physics 105A, video lecture 8. So let's review and then move on. We got some really great material today. But by way of review, we'll just remind ourselves we're solving Newton's law, and we've gone through discussion of what a force is, what a vector is, accelerations, inertia, so that we finally brought it down to into the one-dimensional case. So we're doing Newton's law in one dimension, and then we see that we can have different types of forces. The most general force is position, velocity, and time, and we did some examples. So the simplest example, and very important, is just the constant force. Then we did explicitly time dependent. We did explicitly velocity dependent, and that free fall with friction discussion. But then we finally arrive at force as a function of position only, of which of course this was an example here. Trivially, this is an example of force of position. So we get the force as a function of position only, and we immediately discover that we can introduce a potential energy function. So we introduce the potential energy function, integral of the force, and these are just integration variables because the argument of the potential energy is the upper boundary, A is some constant. And with the potential energy function, I'll write this out, potential energy. We discover that we have conservation of energy. So from here, we discovered that 1/2 mass velocity squared, so kinetic energy plus potential energy is constant in time, and so that's the law of conservation of energy. But it's not just that, conservation of energy in one dimension, but it's the reduction of the differential equation from second order to first order. So second order differential equation and over here it's a first order. Which is great. Because what do we really want? We want to solve the thing completely, so we want x of t. So we've gone from the acceleration to velocity. And we're going to do two things now. We're going to learn how to solve this thing, the interesting technique for solving this, give it a potential energy. So the first thing we'll do is discuss some potential energy functions, and then we'll discuss how to solve this differential equation. This is where we left off last time. So examples of the potential energy. Potential energy. Well, we'll start with our constant force example. So first one, we'll just say U of x is equal, in fact, sorry. Start with the force. So F is equal to minus mg, because that'll be our free fall example we'd like to come back to. And we've got, say, an x-axis here. And if we want to get the potential energy, minus negative mg dx prime from x0 to x, or from a to x, whatever you want. Let's keep it like this, a to x. And what do we get? We we get mg coming out of there times x minus a, or mgx plus some constant. So that's the first one. And if we graph this, we have some constant somewhere. I'll just put it right here. And we have this function with a constant slope. Good. Now, we're going to go through all the powers of x, in fact. This is the first power. It's interesting discussion of x to the nth power. But my next example, since this is free fall and gravity, let's even put this right here. Free fall, well, I don't have to mention that right now. But I'm going to go straight into a higher level gravity, namely Newtonian gravity. So next, well, this is also Newtonian gravity, but I'm talking about Newton's law of gravity. Gravity. So good, you saw this in Physics 4a, and I'll begin with the general form where you say the force is G M M over r squared attractive. So in this case, you're in space and you want to later on discover the laws of planetary orbits, just orbiting bodies in general, central force problem. But for now, we want this in one dimension. In one dimension, we can have F is equal to minus, I'm just going to use the letter K divided by x squared. And we'll see in a moment the negative sign tells us that it's attractive. So what we'll do is just the same thing we did for the free fall problem with a constant force. We will just integrate. So the potential energy, note minus sign signifies it's an attractive force. But I'll prove that in a moment. So we want to get the potential energy. So here, u of x is equal to minus integral a to x. And now remember the rule is k over x squared dx, a little prime here because the argument is up here at the top of the integral, and that's just an integration variable. And we get minus k, the antiderivative of 1 over x squared, minus negative, so we get plus k. The antiderivative is negative 1 over x, evaluated from a to x. And the convention here is to send this out to infinity, and we end up with minus k over x. So there's our potential energy for Newtonian gravity. Yeah, and right now it says point masses, and apparently the center of potential is also at the origin, so we're going to have to talk about that a bit. But the next thing to do is graph this. So now graph u of x equals minus k over x. So here, we're going to quickly see that the minus sign means we're always under the axis, and let's stipulate x is greater than 0. So that's the potential energy function. And the next question is, what's the relation of these two potential energy functions? Because this is Newton's law of gravitation, should be very general. And we're going to spend a lot of time studying this later on, but we're already starting now. So, what is the relation between these two? The two potential energies. That's the question. And what we have to realize is that we know a little bit more. So this is just the one-dimensional example of this. So we could say K is G times capital M times lowercase m. So we have M equals the mass of the central body, lowercase m is the mass in the problem. Same one as up there. And we have to imagine there is a finite radius of the central body. R equals the radius of the central body. And then this lowercase g, which is our 9.8 meters per second squared here on Earth, is equal to capital Gm over capital R squared. See, so under those circumstances, we can relate these two functions very nicely. Namely, this straight line is essentially the straight line that is tangent to our curve there. Get another color in here. So this straight line here is what I'm going to have you guys expand as a perfect little homework assignment, because we've been talking about Taylor expansions. And so what we want to do is the following. So I'm going to write here homework. You want to calculate u of x is equal to u of x0, that's just a constant, plus u prime, let's not call it x0, once more, u of r, so that's just a constant, that's right down there, plus u prime of r times x minus r. I'm going to erase here, I'm going to keep going. Plus u double prime evaluated at r, x minus r quantity squared over 2. And what you'll find is this u prime of r times x minus r really gives you the slope. This is a point slope formula, so you're just getting the slope of that curve there, and these two can be identified with each other. What that means is if you're close enough to the surface of Earth, this curved function is approximated by that straight line. Shifted. The straight line is shifted. So you're going to calculate that, and you'll be able to relate this u prime of r to these quantities here. You'll get a perfect consistency check. Basically, this u prime of r is going to be your m times g, okay, for this function right here. Your u prime of r has to turn out to be m times g. And it will. So just to complete this thought here, show that u prime of r is equal to mg. That's the relationship between these two. And then what you'll see is this u double prime of r over 2, that is the correction And this x minus r right here, that is the same thing as the x up here. It's the distance from the surface of Earth. So if I call the tabletop here the surface of Earth, then x minus r is, give it a new name, right? It's just the distance from there. So that's a nice reconciliation between these two laws, bringing everything together. Okay, good. What else? Show that u prime of r is equal to mg. It's just 1 prime. And this is the quadratic correction to the linear term. And that quadratic correction will tell you how far away you can get from the surface of the central body and still essentially be allowed to use the linear term. Okay, so I think you'll enjoy that. Let's now talk about the other aspect, and that is, how do we solve? We have that up here? No, I've erased it. How do we solve that differential equation? Okay, so we've got a couple potential energies. There will be more. But next, how to solve the differential equation. Next, solving 1/2 m x dot squared plus u of x equals e for x of t. In other words, solving the differential equation to obtain x of t. What we do is first express x dot as dx dt and solve for it. So first, dx dt is equal to, well, we'll just isolate it. We'll have 2 over m e minus u of x, take the square root, plus or minus. Okay, so that's the first step. And by the way, both signs play a role here. It's not as though we can just throw one away. Okay. Well, that meaning, so that's the first step. The second step is what's called separation of variables. And here what we do is we get the x's on one side and the t's on the other. So here we could say dt is equal to dx divided by root, and you know we still need the plus minus, 2 over m e minus u of x. Okay. And then we integrate both sides and integrate. So the integration is from, say, 0 to t, it could be from t0 to t on the left side, and from x0 to x on the right side. So I'm going to write it out. Let's go ahead and write 0 to t, and then we put a little prime there or use some other integration variable. And on the right side, same thing. Put a little integration prime there as an integration variable. So that would be from x0 to x. Okay. And this is the solution to the differential equation. This is t equals t of x, okay, which isn't the way we're used to seeing it. What we really want is x of t, but to get x of t, we would have to actually be able to do this integral and then invert it. So if it comes out as a known function whose inverse function we know, then we can invert this equation and get x of t. So we'll finally write invert, if possible, to obtain x of t. To obtain x of t. So we're going to do this on our linear free fall type example, because that's one whose answer we actually know already, and so we'll be able to check our answer, make sure it's right. So there's the recipe. So let's call this example. We're just going to take u of x is equal to mgx, okay? And we'll go into this integral here. And we get t is equal to plus minus integral dx prime 2 over m e minus mgx square root, we'll prime there, x0 to x. This one's kind of fiddly. I'm going to give it as a homework. We can see, though, that it should work out, because the antiderivative of this will be the square root. So we'll have square root with x under it, t on this side, and then when we square both sides, we'll be getting the x and the t squared law. So things should work out. I'm going to say homework. Solve this problem to obtain, now in the final analysis, what are we supposed to obtain here? We're supposed to obtain x equals x0 plus v0 t minus 1/2 gt squared. Best to leave the energy unspecified right now. What you're going to get is, because of the plus minus and the squaring that's going to go on here, you're actually going to get plus minus absolute value of v0 times t for that term. Okay. And if you save the putting what the energy is in for last, you'll actually determine, well, what value of energy allows me to come up with this expression. And at that point, you'll have it. You're going to have that square root garnished with some stuff. And very important, remember, you have to evaluate it at the top, x, and then at the bottom, the x0. That's how the x0 is going to come into this problem. The v0 will come in with regards to that energy there, okay? So yeah, you don't have the v0 in there yet, but you'll see that once you can bring it into this form, and then you can declare victory. Good, so that is tying everything together. Okay, so what do we have? We have the formalism of conservation of energy seen as being a differential equation, and we can go through these steps, separation of variables, and finally arrive here at this answer. So that's a good concrete example of one that we know. What we want to do next, and this is a longer discussion, may go over into the next hour. We want to investigate, consider a whole class of potential energies u of x of this form. U of x is equal to some constant times x magnitude to the nth power. And we'll specify what n can be, but n can be quite a lot of different numbers. It could definitely be all the positive integers, but it could also be, it could actually also be negative integers. Okay. So that's a very general form. And of course, I could put a subscript here, u sub n and b sub n, because the letter b is always going to have a different dimension depending upon n here, right? But this is potential energy, so it's energy b x to the n. So we're going to start working on this and graphing it. So let's do that. Let's just graph a couple for starters. And for n equals 1, clearly it's a straight line, goes through the origin. Because it's the absolute value, it goes like this, okay? So this is n equals 1, and for n equals 2, let's use red. We know our parabolas. Okay, so there's an n equals 2, that's a bit crude. And what you'll see, oh, let's even put an n equals 1/2 in here. N equals 1/2. So these are all potential energy functions. They've been constructed to have a local minimum at the origin. For n greater than 0, all u sub n, I could put a little subscript there, have a local minimum. Actually, in this case, a global minimum. I'll just say a minimum at the origin. At x equals 0 is our x-axis. Okay, so far so good. Let's erase this. So what about higher values of n? What's the tendency if n gets large, 5, 10, 20, and n smaller than 1/2? You can see for n to the 1/4 power, it would be, as I'm tracing here, for n to the 4th, it would be flatter. So larger n's make it a flatter and flatter parabola. And there's an interesting limiting case where if n goes to infinity, you end up with a square well. So I'll put that as a note. Limit n goes to infinity of u sub n of x is a square well. You may have studied that sequence of functions in a mathematics class. In fact, just consider, so forget the b and the fact that this has dimension, just consider consider f of x is just equal to x to the n. Here I'm going to use a little more room over here. So we've got f of x, x to the n. So now we're just dealing with numbers. And let's just do x greater than or equal to 0. In that case, here's 1 and here's 1. And n equals 1 goes through 1. For all of these, 1 to the n is equal to 1, right? So they go like this, and the higher the power, the flatter this gets. So you can always find an n big enough to sneak under any low value here you want. Okay, so that's what we're saying with approximating a square well. For n goes to infinity, this thing is arbitrarily flat and then shoots up. And for 1 over n going to infinity, or in other words, 1/2, 1/3, etc., you've got the same thing on this side here. And they all go through 1, 1. Okay. So that's an interesting set of functions. Now, the linear case, n equals 1, we've already talked about. That's our constant force potential. The quadratic case you guys may recognize as well for the Hooke's law and the potential energy of a spring type of situation. So yeah, we have a couple of powers that are very important, and we're just going to look at all of them. And what I want to do is this integration for all of them in, so to speak, in one fell swoop. Consult the clock here. Okay, perfect. So square well via this. You can also play around with the calculator and see what, 0.99 to the 100th power looks like. Okay, no matter, if you choose a number arbitrarily close to 1, then you can find an n, a large n, that will make that number to the nth power arbitrarily small. Okay, so that's something to remind yourselves of and play around with a bit. So let's go ahead and do that integration. Should we put any notes here? Leave some room, right? Write some of the stuff down that I was just telling you, especially after you play around with it and remind yourself of these properties. Okay. So now we're just going to do this quadrature, as it's called, this integration again. I need some of these graphs. Well, here we go. So I'm going to go ahead and do the case x, u of x, some positive n, 1, 2, 3, what have you, okay? So that's what we're looking at. We have u of x is equal to b x to the n. And what about the energy? Remember, we have 1/2 m dx over dt squared plus u of x is equal to e. Well, when the velocity vanishes, that's when u of x is equal to e. U of x equals e, comma, when dx dt is equal to 0. And in a scenario like this, you can say that's when we come out to plus or minus a. So we're here, and then u of x, or u of a, is equal to e. So therefore, u of x equals a is equal to e, and that means that e is equal to b a to the n. By the way, that's also how we're going to get rid of this absolute value sign, because we have a symmetric function in each case. We'll just restrict ourselves to the positive axis. Okay. So now we're going to go back to t is equal to plus minus dx prime 2 over m e minus u of x square root x0 to x, or a to x0. Yeah, x0 over x, like that, little prime there. And what we're going to ask about is the time it takes to start, say, or to start at A, go to negative A, and return. Okay. Imagine this is a potential well, and we have this V being equal to 0 at the endpoints. Okay. So this is really the T of x for a motion between negative A and A. So let's actually put this right here. Based on this discussion, okay, it's very important. Note that the motion is restricted to negative A less than or equal to x less than or equal to A. In fact, what we're talking about in a case like this could be an oscillatory motion. Okay. So the example we did before with the free fall potential, that was not an oscillatory motion, but here we're restricted between minus A and A, because that's when the velocity vanishes. So here you would have the velocity vanishing. Here you would also have it vanishing. In fact, comma, because dx dt, let's put that expression up here again, because dx dt is equal to 2 over n e minus u of x. It's got the plus minus here as well. And in fact, now we know what the plus and minus sign is. The positive sign refers to positive velocity, so moving from left to right, and the negative sign refers to a negative velocity, in this case moving from right to left. Okay. So yeah, this whole development is really important, and now we go into this integral expression to solve it, and we can ask, what is the period of that motion? What is the period of the oscillatory motion? Namely, the oscillatory motion between A and negative A. That's the question, and I think that's what we're going to end with. I'll answer that. Center the clock once more. I'll write that, and we'll solve it next time. So to get the period of this motion here, we have to see that we're going from A to minus A and back again. A to minus A and back again. So picking up with the period of the motion, we'll say period T, we'll use capital T, is equal to 2 times this integral minus A to A. Okay. One of the signs is for going there, and one sign's coming back. But instead of the x0 to x, now we'll say minus A to A of, yeah, I'm going to use this general expression, e minus u of x square root. And if the potential is symmetric, we can even take 4 times 0 to A equals, so if u of x is symmetric, then we can take 4t equals 0 to A dx 2 over m e minus u of x square root. So this is the expression we're going to work with next time. That'll be a period of an oscillation in a potential with a local minimum, right? And if the potential is symmetric, well, I've kind of assumed symmetry by minus A to A, so that's fine. That's fine. Okay, good. Next time what we do is we take this expression, which is very general, and plug in this potential right here. So we'll already have an expression for the energy, and we'll now be able to get rid of the absolute value sign because we're only on the positive x-axis, and we'll get a very interesting result. Okay, good. See you then.